Bismillahirrahmanirrahim. So we are back with our next lecture in coordination chemistry, that is crystal field theory in coordination complexes. Crystal field theory in coordination complexes. इससे पहले हमने ब्रीफ में डिस्कस किया था the valence bond theory. So crystal field theory in coordination complexes. यहाँ पे हम इसके डिटेल में नहीं जाएंगे. We'll go to the basics of it because we are looking into the objective type examinations. So so crystal field theory, basically it was initially proposed to explain the optical properties of complexes. Optical properties, number one. तो कोऑर्डिनेशन कॉम्प्लेक्सेस की जो ऑप्टिकल प्रॉपर्टीज है, लाइक देयर एब्जॉर्प्शन स्पेक्ट्रम, देयर कलर, तो उनको एक्सप्लेन करने के लिए इट वाज प्रपोज. बट देन लेटर स्टेजेस इट प्रूव्ड वेरी यूजफुल इन एक्सप्लेनिंग अदर प्रॉपर्टीज ऑफ कॉम्प्लेक्सेस, लाइक magnetic moment, magnetic property, like the energy, stability, reactivity of complexes, reactivity of ligands, and other things. So this was the basics of the crystal field theory. अब crystal field theory में होता क्या है? Basically, one of the aspects it now can explain is that the bonding between metal and the ligand. अगर हमें याद हो, as per the valence bond theory, the bond between metal and ligand is a coordinate bond. It's a covalent coordinate bond. Covalent coordinate bond. But as per crystal field theory, bond between the metal and ligand in a coordination complex is an ionic bond or electrostatic. Or we should say there's an electrostatic interaction between the ligand and the metal in a coordination complex. Take. So that means now these ligands and the metal, they actually interact, they behave like point charges. So each of these entities behave like point charges. जब point charges की बात होगी, that means, so we have 2 point charges of metal and a ligand, and then they interact to form the metal ligand bond, and then in this way the complex gets formed. That means they are obeying the Coulomb's law. Coulomb's law of electrostatic forces. The charges between the two forces. The two charged particles, point charges, they interact through this interaction is governed by the Coulomb's law. Fine? Now if the ligand, a metal, we know that it's a positively charged entity. So ligand can be either anionic, इसमें नेगेटिव चार्ज होगा, और it can be a neutral one. क्योंकि न्यूट्रल ligands हमें पता है कि ligands can be neutral, they can be ionic. So if they are anionic ligand, that means we can have ligands like fluoride, iodide, cyanide, and so on, negative charge. So these negative charged, they interact with the charge on the central metal line. So this is a purely ionic interaction. So this is ion-ion interaction, this case. So this is an ion-ion interaction between metal and ligand. And the next case, when we have a neutral ligand, which is in the coordination complex, which is approaching towards the coordination complex, the ligand can be water, a neutral ligand. It can be ammonia, and so on. हम जानते हैं इस पे lone pair होता है neutral ligands पे. So through those lone pairs, now we have this ligand approaching the central metal line. That means the interaction takes place between the lone pair and the metal. That means the interaction now between the ligand and metal is ion dipole interaction. ठीक. So this is all about the basics of the crystal field theory. Now, important why it is called as a crystal field theory. Now, इसमें थोड़ा सा basics. We'll go into the basics of why it is called as a crystal field theory. So as per this theory, Let us go straight forward to the complexes. We have an Ml4 type complex, and then we have an Ml6 type complex. That means between metal and ligand there are 6 bonds. Between metal and ligand we have 4 bonds, that means 4 ligands. So 6 ligands. So this is octahedral complex denoted by point group OH. This is your tetrahedral complex denoted by TD. Let us take only these two. There are scarce planar, there are other things. So let us go to the basics. Now, as per ligand field theory, how this 6 coordinate complex is formed, that means we have a met line at the center. 6 ligands are approaching from 6 sides. Of an octahedron. Let's show it like this. So these are 6 ligands. So during their formation, the 6 ligands are approaching the central met line from the 6 corners of the octahedron. 4 on the plane and 1 above, 1 below, that makes the octahedron. So at the initial level, all these are equidistant. So the energy of all these ligands is same. और जो इस पे orbitals है central met line पे, we know there are the d orbitals, and those d orbitals, they are dxy, dyz, dzx, and then we have dx square minus y square, and we have dz square. तो ये जो orbitals है, that means their electron density is between x and y axis. यहाँ पे between y and z. Here the electron density or the lobes, they lie between y and z. But in these two orbitals, the electron density is purely along the x-axis or y-axis. Here it is along the z-axis, and some along x and y. So that is they are lying along the axis. Fine. Now, as the ligands approach, they are getting closer. That means इस पे we have orbitals. I will show it like this for understanding. These 5d orbitals, they are on the central met line. So among these 5 orbitals, they are in between the axis, and these 2 orbitals are along the axis. We know all these ligands in the octahedral complex, they approach along the axis of the coordinate system. So if you have a coordinate system here, this is your, let us say, z, this is y, and this is x. Sorry, this is z. Let us say x, and this is y. So all these ligands in the space, they are approaching through the axis. That means जो ligands along the axis है, they are actually जो ligands are approaching along the axis, जो orbitals along the axis है, they will feel strong interelectronic repulsion. There will be a repulsion between the electrons in these orbitals which are along the axis, located along the axis or oriented along the axis with the electrons on the or with the charge on the ligands. So this interaction will lead to the repulsion, and that repulsion ultimately it will lead to the splitting of these. क्योंकि ये वाले जिनका lobes along the axis है, they have a greater repulsion. These orbitals which are in between, they have weak repulsion. That means now when the ligands are very closer to the metal, now the d orbitals will split. तो हम इसको ऐसे दिखा लेते हैं. We show it like this. So initially all the 5 orbitals, they were of same energy. So once they approach closer to the complex, we have this type of situation existing. So 3 orbitals which will come which are in between the axes, they are not facing directly the ligands, so they will get raised in the energy from this equilibrium position. So they'll get raised in the energy. And when those orbitals which are in between, which are facing the ligands along the axis, they will feel greater repulsion, so they are raised in the energy. So dz square and dx square minus y square is raised in the energy. While as these orbitals whose lobes are in between the axis, they will get weak interaction, rather that interaction result in lowering of energy. So these orbitals, they will get lowered in the energy. This is raising is by this raising, this is equivalent to 2 by 5. Okay. So they are raised by, there is 3 by 5. So they are lowered by 2 by 5. This is 0.6 and this is 0.8. At this energy gap, this splitting of the two orbitals, this energy difference between them is denoted by delta 0. This is called as octahedral crystal field splitting. So now it was because of the orientation factor of the ligands were approaching along the perfect axis, and the ligands and the orbitals are oriented along this. It results in the splitting of the ligands. So we have 3 ligands on the which are at the lower energy side. So this is called as T2G set, and the above one, this is called as a EG set. So this T2G EG, this is called as a crystal field splitting. Fine. Now tetrahedral के case में we have a reverse. So this is the case of the octahedral. Now tetrahedral के case में, in case of tetrahedral complexes, we know that जो complex होता है उसमें जो ligands है, they are oriented in between the axes. They are not oriented along the जो हमारे पास 3-dimensional coordinate system उसके axial, they are not oriented along the axis. Rather, ligands are approaching in between the axis. In between. That means जो orbitals जिनकी orientation, जिनके lobes which are oriented in between the x, y and z axis, they will have greater repulsion. That means they will get raised in the energy, while as rest of the orbitals which are along the axis, they will get lowered in the energy. That means the behavior in case of tetrahedral complexes will be a reverse. 3, 4 and 5. So we have the case of so 1, 2 and 3, and then we have 1 and 2. So this is dx square minus y square, and this orbital is dz square. So this is raised xy, this is raised yz, raised zx. So these orbitals which have their lobes in between the axis, they are getting more repulsion. That's they're getting raised in the energy. Whereas these which are lobes along the axis, they're getting lowered in the energy. So that means now we have the case of 2.5 here and 3 by 6 here. So this is 0.4 delta 0. So this is 0.6 delta 0. So the crystal field splitting is reverse. Or दूसरा, the extent of splitting is very small in case of tetrahedral complexes because there are only 4 ligands which are approaching towards the centimeter line. While in this case, octahedral complexes, this crystal field is splitting. Sorry, this is, I have shown tetrahedral, it's tetrahedral, delta T. Sorry. It's the reverse of octahedral, but then it's delta T. So this is delta O, octahedral. So this is delta T and this is delta O. Since the number of ligands are more in case of octahedral complexes, the gap, the splitting is more, while as in case of tetrahedral complexes, the nature, the types of ligands are only 4, their only number is 4, so the splitting is less. Second, since the orientation factor is also there, so because of the orientation factor and the number of ligands in overall, the crystal field of splitting is more in octahedral complexes. And in case of tetrahedral complexes, because the number of ligands are less and orientation factor is not there, that was dominant. So because of these two, that there is less crystal field of splitting in case of tetrahedral complexes. So the crystal field of splitting in octahedral complexes is more than tetrahedral. And crystal field splitting, if it is more, that means complex is more stable. Now, last point पे, जो हमारे पास ligand, there are ligands which can create this crystal field splitting more. So it depends on the nature of ligand. जिस type का ligand होगा, accordingly the crystal field splitting will vary. So based upon that, this point that there are ligands which can cause greater crystal field splitting, so which called larger crystal field splitting. So they're called as a stronger field ligands. Stronger field ligands. And there are ligands which have low crystal field splitting effect. They're called weak field ligands. So based upon this behavior, ligands can be arranged in some order. So based upon the power of ligands to cause the crystal field splitting, ligands can be arranged in some order. For example, we'll keep here iodide. मैं बस 2-3 examples यहाँ पे दिखाऊंगा, ज़्यादा नहीं. This is fluoride, and then I will keep here OH. Then I'll go straight forward to ammonia. Then increasing order. So just stop it here. I can further keep here some more examples. So then I will go to straight forward to NO2, moti points. Then I will go to CN negative and then CO. So arranged these ligands जो main complex में usually हमें दिखते हैं. I have arranged them in some order. So those ligands are on this side, they are called as a weak field ligands. They have a weak crystal field, weak field ligands. Weak field ligands. और जो ligands इस side में हैं, they are called strong field ligands. मैंने बहुत सारों को इसमें skip भी किया है, just to get an idea about the crystal field theory. So they are called strong field ligands. That means when they are present in the complex, they will lead to greater crystal field splitting. And when these ligands are present in the complex, when they are present in the complex, they will lead to less crystal field splitting. That's why they are called weaker. And when they are ligands in the complex, they will lead to greater crystal field splitting. That's why they are called as strong field ligands. तो ये तो हो गया एक general overview of crystal field theory at this level. तो आगे की क्लासों में we'll try to get some more. We'll see as per the syllabus requirement. So this was the basics of crystal field splitting, where in nutshell, the ligands, they behave, ligand and a metal, they behave point charges. So the interaction between them is electrostatic. So we have an ionic bond between them as per the theory. And then when the ligands approach the complex due to the complex formation, the degeneracy of the d orbitals, they are lost. That means the d orbitals are split into two sets, T2G, EG set, and accordingly in the tetrahedral, octahedral, they are reversed. So that gap which is created, that's called crystal field splitting. So the stability of complex is designated by that crystal field splitting. So this is all about the crystal field theory of coordination complexes.